Hello, everybody, and welcome as well. Thanks for joining us on this seminar today. As Tim mentioned, my name is Brian Palmentier. I lead the Transmission Distribution Interactions group here in our Grid Plane Analysis Center at NREL. And today I'm going to talk to you about some really exciting work and capabilities we have with Helix. I wanted to acknowledge that this has been a really strong collaborative effort across three national labs, ourselves with Pacific Northwest National Lab and Lawrence Livermore National Lab. A few others have also, a number of others have also been using it, but this is sort of the core development team. So to kind of start things off, let's sort of set the stage. Electrification, digitization, DERs, a number of other trends that we're seeing in the energy and grid industry are increasingly bringing together things that have historically been separate, different domains. And this prompts a whole range of questions. I'm not going to read through all these, but for example, how does distributed energy resources interact with the bulk system? Can they be relied upon? Are they going to behave in an understandable and supportive way during faults? Are there opportunities for them to actually provide some of the energy resources, some of the capacity resources, some of those other things that are needed? And even beyond just the grid, when we start to think about interactions with the gas system, things with transportation, building environments, lots of different aspects there. And even more technical aspects like communications and some of these other controls become increasingly important, then those become increasingly relevant. And as I mentioned, these connections to other domains, it's really like the grid plus all these things, or in some cases, it may just be synergies between those different domains beyond the grid. These are all really key pieces of connections that are increasingly relevant as we look about today. The trick is that simulating these types of interactions, we're now starting to try to capture phenomena that are across historically separate domains. And in particular, there are many very well-established, well-trusted tools in kind of each of these different isolated blocks. Here's four examples. You can imagine a lot further for things like on the grid, transmission, distribution, control, and communications, with a number of important grid-adjacent technologies, transportation, water, gas, and even just the interconnection between those without the grid. And the trick is they're all running in their own little silos of excellence, if you will. Great folks, great analysis, tons of capability, but this future that we're moving rapidly towards really requires bringing them together. And that's kind of the goal of what Helix is trying to do in co-simulation environment, is it lets us take two or more existing tools, not necessarily changing their inner workings whatsoever, but then coordinating data exchange during the simulation. So at each time step, if you're simulating a year, maybe it's every hour. If you're simulating a faster phenomenon that lasts a couple of minutes, maybe it's every second, or super fast stuff, maybe every millisecond or faster. Those exchanges so that the multiple models are acting as one big, tightly integrated co-simulation. So just to make sure we're all on the same page about what that means, we'll talk about kind of conceptually, if we were imagining a transmission and distribution co-simulation happening, we would have a tool for transmission, a tool for distribution. Those could be any number of different existing tools. And now the first thing would be to have a thin software wrapper around those that allows the data exchange and kind of pausing the time. And then those interfaces would connect with a co-simulation hub to manage that exchange and timing. Of course, this could be done with a lot more tools, lots of different examples of the same thing, say multiple different distribution simulations simultaneously to meet the same scale as transmission, or bring in any of those other domains. And so Helix is a co-simulation framework, one of the most advanced, high performance, that allows us to take these best-in-class tools and do this breakthrough integrated energy system analysis. There's a lot of capabilities. We'll touch on some of those here, but I want to make sure to list some of the big highlights pieces here. One of the key things is very highly scalable. You could do this for small problems on your laptop, which could be a couple of different models together, could be a few dozens of models together. But if we start to think about really, really big scale analysis, like say one of the interconnects in the US, the Eastern Interconnect or Western Interconnect, with lots of feeders and lots of different individual homes or loads or commercial entities, like the number of models or federates that would need to get brought in can be humongous. And Helix is able to handle that whole scale, which is unique and allows you to build something to do a small test and then rapidly scale up and add more and more complexity. It's also open source. We'll talk about some of these other unique features, runs across platforms, has a lot of APIs, ability to write software in just about any language you need to wrap your tools, and especially those that are extremely common. And also connections to FMI, which is a fairly established for certain classes of controllers and other modeling simulations. On the left, you'll see some links. We'll come back to those later in terms of if you want to access the software. And because Helix brings together existing tools, it also matters that we have, you see on this bit busy chart, a very large number of both commercial and open source tools that have been used with Helix and therefore already have that software wrapper in place, typically open source, although a few may not be, that allow you to get these connections going so you can do a co-simulation without even having to write that wrapper if you're working with an existing tool across all these different domains. But let's take a step back. We've introduced a little bit about Helix, a little bit of the big picture motivation, but what are the real opportunities and benefits for using a co-simulation? The first one is, we sort of highlighted already, Helix lets us use existing tools, if you will, to stand on the shoulder of giants, as you see this little Lego man doing here. And that allows us to take advantage of all that effort that's gone into these subdomain tools that they're trusted by stakeholders, already in use. There's people who know how to do them, build the models, those data sets exist. Those can continue to improve, but we can then focus on the glueware that pulls these pieces together and allow this co-simulation to happen. This also enables modularity, which is the idea that you could trade out. Let's say for initially you were using one power flow model or production cost model, you could trade that out for a different tool without necessarily changing the rest of the simulation, co-simulation ecosystem. Another benefit is that well, before we jump into those, the two main goals we've alluded to earlier for co-simulation are keeping everything running in sync. So kind of a bit of a traffic cop to make sure things are moving at the same pace. And then the other part is delivering data kind of as a postal service to make sure that the right data gets to the right place in the right time. As we highlight there, that means that the co-simulation environment itself isn't necessarily doing any modeling, rather it's bringing models together. So all of the capabilities and behavior come from what you're bringing in, and this allows that to be done in an easy way, in a scalable way, in a repeatable way, in an interchangeable way. And this is what the other benefit is. A lot of folks are like, oh, actually, I use this tool and that tool. I'll just write a little custom wrapper. We'll just kind of stuck them together. It'll work out great. Surprisingly hard to get that right. We've, a bunch of really smart folks in the National Lab system have started down that path and realized, wait a minute, actually, there's a lot more nuance to this than I realized, and have been able to convert over and very rapidly use Helix to pull together these tools in a way that really lets them avoid some of those pitfalls. And then also provides a huge benefit of being able to zoom out, to think ahead, to think about how this framework could make reusing these and future analyses with different tools much easier, as well as to add in, oh, wait, what if I did want to add in that extra control loop in addition to this piece here? Or what if I started on the grid now I wanted to bring in transportation or buildings? With a co-simulation framework, you can do that without having to kind of scrap or rework all the old pieces. Effectively, we've done the hard part for you. Now, the other thing is this allows some modular development and debugging. So early on, you kind of agree upon what data is being exchanged between the different tools. And this enables us to start with really dummy examples that verify that interface, and then incrementally add in one real model and eventually both real models where we kind of work out the different kinks. And in the meantime, the quote unquote fake tool can be providing the same exact type of data, maybe not through simulation, but just by reading from a file or other approaches. We have built in a capability to support that, to enable the real model as it's being tested to be looking exactly like it would in a co-simulation environment. And this really enables some important development and debugging capabilities during testing phases that have proven to be very, very valuable, especially as you start to scale this up into dozens or hundreds or thousands or arguably even millions, which we've done a little bit of work on as well, of these different tools. The ability to work in this way allows a team focused on one model to really get things right, while another team in parallel is getting things right on a different model. Another benefit is this performance and scalability. There are other co-simulation frameworks, but none of them have the same level of scalability as Helix. And a lot of that comes from the H in our acronym, this hierarchical broker. You can see a broker is the hub, as we described, where multiple different software tools would connect, and it helps manage the data between them and the timing. Because really big problems, you don't necessarily need the data exchange all the way across all of the different federates, all the different simulations. It's possible that a lot of the interactions, let's say it's a distribution system with buildings and controllers, that interaction is going to be local. And having a sub-broker that can manage that type of interaction and then a subset that gets shared through a master broker to other parts of the simulation can really help with the performance and scalability. The other thing that Helix enables is any mix of different solver types. Rather than forcing everything into, say, a mixed integer linear programming paradigm, you can also use differential algebraic equations, other engineering tools. Whatever tools are currently used, you don't have to force them all into the same paradigm. You can kind of leverage whatever's best for the different subproblems. When we talk about performance, don't just take our word for it. Some non-affiliated researchers in Europe did some comparisons among a number of different co-simulation tools and found that the solution time here on the y-axis scaled by far the best with Helix when you're taking advantage of the multi-process capabilities there. You see, some of the others couldn't even get to some of the larger scale problems in any reasonable level of simulation time. Another benefit that is increasingly seeing interest in is the idea that by having the models running separately, this also means they don't all have to be done by the same team in the same organization in the same facility. So whether it's a cross facility where maybe the transmission modeling is done in one place and the distribution modeling is done in another place, or even if it's totally different organizations, where say like a bulk system, transmission system or independent system operator is modeling a piece of the system, while say individual distribution utilities or even things like third parties, aggregators, independent power producers are providing different aspects. They can keep their own models internal with the experts who know how to do them and the data that may be sensitive, and just exchange the interfacing data, say where the transmission and distribution come together or where the buildings comes into the grid or whatever other connections are relevant. Just that little bit of information needs to be exchanged rather than the full model, because then we can use a cloud or direct VPN type connection to not allow groups to kind of keep data to themselves. So Helix is not just a brand new thing. We've used it for a ton of different pieces. You can see dozens of projects here, some in the national lab space, some with commercial entities like New England ISO, SIME, Eaton, as well as a number of research organizations, utilities and universities, research organizations we've been able to connect with too. Lots of different aspects, transmission distribution we've highlighted so far, as well as all these other pieces, transportation, controls, natural gas, cybersecurity, even folks trying to build up training data for AI models have used Helix as a way to get a lot of simulations done and then feed that into training data. So lots of different use cases. We're going to take a little chance now to dig a bit further into what Helix does and kind of what it enables and some of its other unique capabilities. Exchange data, we got that part. But one of the other unique things about Helix is that it recognizes that there are two different classes of data that need to be exchanged in these co-simulation environments. The first one are things like physical values. In the case of a transmission distribution system, if you had this thing in reality, then somewhere in a substation, the voltage on one side, the transmission side, and the voltage on the distribution side, they're going to match. That's the physics. That's how the way things work. So getting those physical boundary conditions right, it looks a little bit different than some of the other aspects we'll talk about in a second. So for example, maybe the voltage and the load being exchanged between those are physical values. And we allow tools to iterate to converge on those boundary conditions before advancing time, which is a unique capability. It allows the multiple different pieces to get the physics to be totally right before you try to move forward. Here's an example of doing just that type of work. In transmission distribution for like a faster dynamic consideration, where now we're looking at a fault, some kind of a short or some other kind of challenge on the bulk system. is being modeled in a tool like PSSE that's often used for those scales. You'll see a drop in the voltage, and then over time it tries to recover. On the distribution side, using something like OpenDSS or GoodLabD or a commercial tool like SIME, we would be able to capture some of the voltage phenomenon across space that are missing in that representation in the bulk system. And exchanging and trying to capture those two together can create some really interesting effects. Here's an example where we did this on a recent project with Puerto Rico, part of the Puerto Rico 100 study, where we're looking at how the high amounts of distributed resources can really affect the stability of the transmission system. And if you draw your attention to the right-hand figure, you can see this blue line, and that's what a very well-designed and very carefully assembled model and tool for the transmission system alone. This included representations of those DERs, but it still didn't have that voltage diversity. And you can see in this case, the voltage temporarily dipped, but then very rapidly came back. However, when we did co-simulation with that same tool, but now replacing those aggregated models of the DERs with a full representation of the distribution system, we can see that the difference in voltage as you get further and further away from the substation and other phenomena cause really different responses. In this case, a fault-induced delayed voltage recovery, where stalling motors kept the voltage low for a long time before it finally ramped up. If you have all the right models tuned on the bulk side, you might see some of this behavior, but you won't be able to get all that voltage diversity and therefore wouldn't capture the full phenomenon of what's seen on with this co-simulation. So coming back to Helix, we just talked about physical values. The other class of values are those that are messages, we call things that are sent over information and communication technologies, or ICT. And so this is just about everything else. So here's one example where we would have, say, a market simulation, thinking about how DERs are interacting with bulk system markets. And we're seeing, of course, that same physics on the transmission distribution interaction, but now we're including the idea that the market system will be providing dispatch signals to the transmission and then receiving a measurement of the actual generation, which is probably not going to be the same as the actual dispatch, and also not going to be exactly what happened because it's a measurement. Same thing between, say, real-time prices and measured load with the distribution system. So these messages are completely different concept than a physical value. Physical values have to match, would be because they're bolted together. Messages are things that are sent over some kind of communication network and enable us to kind of capture more realism and distinguish what's going on with those. These messages, for example, would have a fixed sort of start and end, sent time and receive time, and as we'll talk about later, can be modified in transit a little bit if needed to help capture more complicated phenomena. So here's an example where we combine these two together. This was a project looking at the Western Interconnect in the US and trying to understand the interactions of getting price signals down to distributed resources to loads directly as devices. And so you can see in the upper chart here that the idea was if there were no retail markets, or if we're just having devices, loads being kind of dumb, doing their own thing, not really just kind of rolling about, there's a big increase in price during the middle of the day. If we do a fairly simple approach of sending the real-time prices from the wholesale market out to those devices directly, such that they're responding, we see this oscillatory behavior where there's a bit of overshoot because a little bit of price change is causing too much change in load, and we go back and forth. If, however, instead we do a retail wholesale interaction, does the co-design market, you have a nice smooth price trajectory. So this was all done using co-simulation with tens of thousands of feeders, a simplified representation of the Western Interconnect, 25 million homes, and a simplified market model. You could imagine doing this research question, applying it to an industry application where we're saying, hey, how do we design this market the right way to avoid this type of phenomenon? Kind of a production cost, but with much more resolution on the distribution side to capture these phenomena. The other thing that this messages allow us to do are to think about controllers. The idea that we're increasingly seeing controls on distribution and transmission could be coming from aggregators, could be coming from local sites, could be coming from lots of different, from DERM systems. And similar to market operations, these are messages that are sent over communications, network communications, in this case, sensor data and control signals, but the same phenomenon can occur here. We've actually used this in the past on a number of different projects. Here's one where we're highlighting a novel control architecture that manages transmission and distribution together. We did a project in the island of Oahu in Hawaii, where we're looking at a very large grid simulation. This is over 1 million electric nodes all the way down to deep in the distribution system, and looking at a number of different advanced controls that use predictive state estimation and machine learning to help manage things out. Helix provided a fantastic way to bring together that transmission model, hundreds of distribution models, and then hundreds of controllers for each of those different distribution systems to make sure this worked and worked at scale with realistic data. The other thing that happens is because we're distinguishing messages, and you could actually do similar things with values, but it's a slightly different use case. We have the ability built into Helix to say, wait, that's a control signal. That may not be perfect. It might take a delay to get there. It may be randomly dropped. You could even imagine modeling, and people have done this work too. I don't highlight it as an example, but thinking about cybersecurity attacks where you're spoofing the data or changing it. We can do those through what we call filters, and we can do that without changing any of the individual tools and models. So you can see in this block diagram, stylistically, the transmission block, the distribution block, the controller block, those are the same. Those models haven't changed. The interfaces haven't changed. But through the Helix, when the data is being exchanged, we can apply this filter to add in some of these non-idealities. We can even do fancier things like, without changing the tools, route that signal through a detailed network simulation as well. Here's an example of where we use some of the COM filters built into Helix to look about how communication delays can impact the response of DERs. So in this case, we have a large number, 42,000 electric vehicles providing frequency reserve. So this is when there's a disturbance on the system, often when a generator goes out, the frequency on the bulk side of the system, the entire grid, may drop until you're able to bring more resources online. And the idea of this is, in addition to bringing resources online, we could also control smart charging behavior of the electric vehicles. And to do that through this automatic generation control signal that provides those very fast control signals to enable this recovery to do better. But the question is, what if that communication system, as it bounces from the wholesale operator, potentially through an aggregator, and eventually out to those EVs, has enough delay in it? And some of the technologies out there could actually introduce seconds or multiple seconds or even dozens of seconds worth of delay. And you can see here on the right that we're able to replicate some of that behavior where the frequency recovery back to the nominal 60 hertz can be significantly impacted if there's a significant delay between these systems. Some of the other capabilities in Helix, this tends to be a bit of a command line type of interface, but there are some web interfaces to help manage what's going on and see what's going on, as well as this command line interface, that's what CLI stands for, is included with Helix that allows a fairly easy way to build up these co-simulations and kind of push go and redo that again as you kind of work through the different pieces. And so this Helix CLI helps with the launching. And that may not seem like a big deal if you're thinking about a couple of different examples, but when we get into hundreds, thousands, millions of simulators, the ability to have a single system that can go out and start all those different simulators as configured, get them connected up with the right hierarchy of brokers and the right messages being exchanged is a non-trivial effort. And this interface makes it a lot easier to do. So let's look at a couple other use cases here, and then we'll wrap up before too long. As I mentioned before, it's not only the grid as the examples we've seen before, but also connections to grid adjacent technologies. Here we're looking at natural gas. This was a simulation that was done where we're looking at the electric system and the gas network kind of at a bulk scale, where the pipeline serving generators, this is common in the Northeast, this was an example done over in Europe, where there may be bottlenecks, particularly if there's a lot of heating demand at the same time of getting that gas to generators. And then likewise, if there's not electricity, some of the systems of the gas system may be compromised, the ability to provide the right pressures. So there's some real synergies between these two systems. And we did a project using Helix and in partnership with NCORD to get those connected. And this actually had multiple purposes. One was to showcase the opportunity to do gas and grid together, but the other was to validate that splitting up a simulation between these two different federates and passing the data through Helix might, there's a potential risk for there to be some not capturing the same as if these models were done together. And so the tool we used in partnership with NCORD, their Sync tool can actually model both gas and grid together. Or what we did in this case was compare that results to passing the same type of data through Helix to make sure that the co-simulation framework wasn't messing up that exchange. And here you can see in the upper right figures that the integrated simulation all-in-one tool versus the co-simulation had the exact performance. It's a nice validation to show that, yes, splitting these things up can still provide the same results as if they're all together. The other thing that can be done, we talked a little bit about how controllers can come in, but sometimes, often in academic or research environments, controllers can be designed and built using a simplified representation of the network. And then you may just stop there. Hey, my controller worked great with a simplified representation of the network. And that simplified representation of the network actually happens to be deeply embedded into our control scheme. However, when you get out to the real world, doesn't matter what that control scheme is, you're probably not going to have an actual accurate representation of the real system. And so it's important to be able to test a controller in a simulated environment with a realistic system that includes all the pieces that were not simplified in the representation included in the controller, as well as in capturing that idea that the models aren't going to be right. You never have perfect data in the field, particularly from distribution systems, but really from any parts of the grid or other parts of the energy environment. And those non-idealities can sometimes be a real Achilles heel for controllers. Helix allows us to take this and in software, put that whatever control it happens to be, whether it's monkeys pushing the keyboard or the most advanced AI control or something in between, and have it look just the same as if it were in a real environment, but rather than having the not exactly as captured in your controller's model, real world, we do that in simulation with, in this case, maybe a distribution system being simulated with a rich, detailed model and all the bells and whistles of phenomenon compared to that simplified model and controller, and really start to understand, does your controller work? What kind of things need to change when you don't have necessarily quite as perfect an information? Other things we've done with Helix include hardware in the loop testing. So Helix has a mode, a switch that can be turned on to make sure that the time advancement isn't the default, which is as fast as possible, as fast as all the simulators allow, but rather locked to real time, meaning when 1 second elapses, a second elapses in the simulation. And we've used this to scale up some hardware in the loop testing. So here's our advanced distribution management system testbed that also can be used to test out distributed energy resource management systems. These are systems that are run at utilities. And in this case, we have real commercial ADMS systems running in software connected to actual hardware devices, as you can see in some of these figures. But that's only able to connect. Now we can do hundreds and sometimes even thousands of devices. But in the real world, there may be millions of these devices. And even if we're looking at a single feeder, it's tens of thousands or thousands, depending on how fine grained we're going. So often the amount that can be done in hardware is a subset of what can be done at scale in simulation. And through co-simulation, we can take that real-time simulation happening things like RTDS and OpenRT connected, providing the waveform signals to some of the hardware devices, but then have those interacting through Helix with phasor-based or other sort of like millisecond or second scale simulations in tools like OpenDSS to capture that broader network beyond what's captured in hardware. Lots of interesting opportunities to have these Helix as an exchange mechanism between a subset of the devices with the rest being simulated with software-only pieces. So that's what's done in ADMS testbed, in NREL's Aries platform, and other places. So if you're ready, if this has hopefully piqued your interest and interested in learning more, wanted to quickly show you some of the resources to kind of get started on this space. And then after that, we'll switch into questions. So the first is that we have a fairly extensive user support offerings. There's a lot of great documentations. Helix in some ways is a bit of a software library that enables pulling all these pieces together, but has a lot of capabilities to make that easier to do. So there's a lot of good documentations. We have a YouTube channel that highlight in depth a number of the projects we just touched on here, as well as tutorials and how-to and getting started aspects within the YouTube channel. The developers of Helix are generally quite available through the Gitter channel you can access through our GitHub repo. As I mentioned before, this is an open source tool, so you also very much welcome contributions from the community, whether that's bug reports, suggestions for improvement or wrappers around tools or use cases or are there new capabilities. Welcome all of those. So user support for those trying to get started, and also very much welcome others to contribute to the project as in its open source nature. We also have currently right now, sometimes comes and goes a little bit with funding, office hours for helping folks debug every other week at this stage. And I hope we can be able to continue those long-term, somewhat contingent on funding. So with that, I think we can open up to any discussions or questions. I've got my email here if you have an additional contact interest, as well as the documentation and code links that we shared earlier, where you can kind of dig in as might be relevant. And so again, wanted to acknowledge that this is a nice joint effort, strong partnership between ourselves at NREL with PNNL and LLNL as well.
Thank you very much, Brian. It was a wonderful presentation. All right, we have a few questions rolling in, and please keep them coming. We'd love to hear what you guys have to have, for Brian. So first up, the first question we have is, can Helix work with real-time simulation like OpenRT, RTDS, etc.?
Fair enough. Yeah, and I think we actually hit that in one of our use cases, but I can elaborate that a little bit further. The short answer is yes. We do this all the time in this example in the ADMS test bed and in Aries of real-time hardware plus software simulation happening here and at NREL. And as I mentioned, one of the key features that enable this is the ability to have a real-time flag set so that Helix doesn't get ahead of itself. It is worth talking about a little bit more in depth, though. Real-time simulations with like an RTDS or an OpenRT tend to need to have really fast interactions with the hardware itself, often in the microsecond level, tens of microseconds, sometimes hundreds of microseconds. That type of really fast data exchange is best handled directly between the real-time digital simulator, whether that's Opal or RTDS or Typhoon or any other of the vendors in that space. It's really where we start to think a little bit broader than that, whether we're trying to pull in either, as we show here, a broader simulation of a network beyond which might be practical to capture in real time in these real-time digital devices, or if it's trying to pull in connections like controllers or other aspects, maybe it's other domains, like a gas system or a buildings model or other pieces, things where running everything at that microsecond scale is overkill, basically. You're not necessarily trying to form all the waveforms and all the nuances across all the phases, but trying to capture a larger scale. And that's where we find Helix being a really big value in complement to that direct connection that is happening between these real-time simulators.
All right, up next, it's a two-parter. Have vendors approached NREL about potentially making this a commercial product? And do you think it could or should be a commercial product, or should it remain an R&D effort?
Yeah, that's a really great question. The short answer is we have partnered with a number of different vendors to include their tools, and people have been very generally excited. A number of the vendors we worked with, they've even gone so far as to make small adjustments to their internal models to improve the way they interact with a co-simulation environment like Helix. They worked out of the box, but there's ways that can be improved a little bit. There is a strong interest in keeping Helix in an open environment, but we are actively trying to identify ways to scale it well beyond the research community. So we've been looking at different venues as to whether that's slightly different governance structures to make sure that we can bring vendors and utility users and consultants and any other parts of that ecosystem together to get behind it as not necessarily a lab-based thing, but a community-based effort. And we've also been looking at opportunities where Helix could be available as a service to different stakeholders, again, on a grid side that could be, say, ISOs and TSOs connecting with distribution systems, but you could imagine a number of other pieces where it might be distribution utilities connecting out with models of the DERs and or loads on their system, or even folks who are developing power plants or gas systems or transportation systems interacting. So at this stage, we have a very robust and very well tested, very well documented and automatically tested as well, core capability and are actively looking to grow that community to include more folks and perhaps a somewhat different governance structure to allow it to go well beyond the lab and have a broader impact. So I'm not sure who asked that question, but please reach out if you're interested in exploring that further. I'd be happy to discuss.
Right. Up next, is co-optimization a part of Helix, or is it only capable of co-simulation? What does it take to use Helix if I want to perform a co-optimization?
Yeah, it's a really good question. And I think it depends a little bit on what we're getting out of a co-simulation versus a co-optimization. And so I want to unpack that a little bit further. And so Helix certainly is extremely well built to do co-simulation. And in that case, we're doing a simulation over time, exchanging data. I mentioned some of these abilities to do convergence. There's even tools to help with that convergence, those kind of pieces. When we talk about co-optimization, some levels of that co-optimization have a similar operational feel. For example, a market operation, which trying to determine the optimal dispatch every 5 minutes, maybe with some hour and day ahead processes as well. The Helix would be well suited to simulating that type of co-optimization with other spaces. So it could be, for example, multiple grid operators, so say two TSOs interacting, or multi energy systems where we would have, say, like a grid operator and a gas operator, a transportation operator, and a building management system operator. Those all have a flavor of operational co-optimization that Helix would be very well suited for exchanging data between those efforts. There's even been some work done on opening up the hood on a optimization engines and exchanging data in terms of like gradients and boundaries and constraints to enable an optimized operational simulation, I guess is a way to say it. So there is some strong co-optimization there. Helix could be forced into use in a more planning, like investment planning co-optimization space, but it's not quite as well designed for that because those tools tend to not be set up to exchange data among themselves in the middle of a simulation. So it's possible to use something like Helix for that, but we actually have some other capabilities, notably MDO for Grid, that are trying to target that, if you will, capacity expansion planning, investment planning, policy design space where the optimization of what's built or what the system is going to be like is changing over time. The Helix may be a little less well suited for that, but is very well suited for co-optimization when the system, the physical pieces are kind of predetermined. They may go in and out as things come in out of service or as a storm comes in and causes chaos. But there may be optimization in that sort of simulated operational context that Helix is very well suited for.
Thank you for that one. Next, are some of the utilities already using Helix across use cases, e.g., dynamic response in case of large generator trip, etc.?
Yeah, great question. I think the right way to say it is there are some utilities and grid operators using this on sort of a pilot or trial type of basis. We're definitely looking to expand that into a more like core part of those operations. But as it stands now, mentioned a number of different things in those examples, but like ISO New England, for example, has done some kind of research where they're looking at, hey, how do the stability behavior with a better representation, a more rich representation of distribution look like? So using dozens of feeder models connected with dynamic simulation. Saw that example in Puerto Rico as well. The Hawaii work, we're looking at different control schemes that was done in partnership with HECO. There's also opportunities to do this not just in that engineering context, if you will, where we're looking at stability and other actions, but also in that sort of techno-economic analysis with the production cost or other types of phenomenon that tend to be a little slower in the simulations in terms of their time steps, but equally important to capture those interactions across different domains. Looking again for more opportunities to connect with people in that space. There's also been some interest, I should highlight, too, where some of the utilities we've been discussing with in California and even a little bit internationally, where co-simulation might be relevant for digital twin type applications as well. The ability to set up and do whether it's hardware or just kind of real-time type simulations of future implementations of their grid, and doing that with really rich detail, but enabling that to scale and to capture controllers or other phenomenon that might be well suited to connect in with Helix in the nice modular way that's provided there. Again, happy to contact and discuss further.
All right, up next, and we still have time for more questions too, so feel free to keep asking them, folks. Does Helix support arbitrary solver, for example, adding machine learning or even human feedback in the loop, or is it only for support mentioned software?
Good question. Helix is definitely agnostic to what the pieces are that are interacting with each other. So certainly can be any types of solvers under the hood with different tools, or any types of, we have some support, as I mentioned, this idea of in co-convergence, where we're trying to get, before time advances, different tools to collaborate. We've built up this concept of helpers that can help drive that convergence to be faster. That's a bit of a framework that could be, and it expanded beyond the types of mostly heuristic approaches that have been used to date. Some are also just kind of fairly simple Newton-style gradient descent. You could also imagine that being augmented with additional support in that space. Helix works, and then sort of on that broader context of like, what if it were like a human in the loop or some other kind of actor in the loop? And that would also be possible. It's a use case we haven't explored quite as much, but it's certainly one that's possible. Because the way Helix works, and this is a little bit deeper in the weeds than this high-level presentation, but basically each of the entities that we call federates that are part of a co-simulation, they request the next time that they want to kind of get data or exchange data. And so you could imagine a simulation that maybe there's an hourly market operation process being simulated, but there's also like a minute by minute simulation happening between DER behaviors as a result of weather, for example. So then the simulation that's capturing the markets might say, hey, the next time I want to get information is an hour from now. But the other simulators that are capturing the faster phenomena might be requesting every minute. And then Helix looks around and says, okay, well, the minute's the time we're going to exchange data because that's the most relevant. Let's make sure all the data gets exchanged here. Hey, market, if you want, here's the data, but you may not need it. Eventually, you kind of work your way forward until you reach that hour after 60 minutes, and then everybody's exchanging data. You could imagine if there were, like, say, a human sitting at a terminal or an AI entity running asynchronously, that they could be requesting time, and then the whole simulation, unless you've turned that real-time flag on, would be waiting until everybody's got the data ready for that next time to exchange. So that would allow something like a human in a loop or an asynchronous AI or other types of pieces to be part of a larger simulation. So hopefully that addressed the question there. Happy to follow up further too if needed, or connect you with others on the team who can dig in deeper.
All right. Could you talk about the software stack used to enable this? What languages or frameworks would one need to know to contribute?
Yeah, great question. There's a sort of two-part answer to maybe even three-part answer to that question. Core Helix is written in C++ using a lot of the modern paradigms. I have to admit, I don't remember if we're using 17 or if we've advanced beyond that, but very recent. So some of the pointer challenges and other pieces a little bit more straightforward. So the core work is in there. There's a number of libraries that are pulled in. I encourage you to look at the Git repo and or connect in through the Gitter channel to dig in a little bit further on those. So if you wanted to be contributing to the core part of Helix, then familiarity with C++ would be very valuable. But because we want to support a number of different software interfaces to allow developers and researchers to connect in without necessarily having to work in the framework of C++, we've actually taken that C++ base, pulled it into having a C-style interface, which has a little bit easier to connect with other libraries and models and frameworks beyond that. So in particular, we've got a very robust and Pythonic interface in the Python programming language, a very nice interface in Julia. There's a nice interface in MATLAB, a number of other nice interfaces that build on top of that C interface and enable the access to all the capabilities without having to dig into, say, C++ or the core pieces. And so if somebody's interested in contributing to either of those kind of core Helix library offerings, then knowing C++, a number of the library stacks, including sort of the modern paradigms, would be valuable. Or contributing to these language bindings, the Python, the Julia, the MATLAB, a number of others. FMI is also in there. It's not really a language, but it's a plugin framework for different abstract control and simulation models. Knowing any of those can also be a big value in terms of being able to contribute. Some of those, as I mentioned, have a little bit of knowledge of how to interact with that C underlying library, but there's still plenty of opportunities in terms of doing testing, doing development, documentation support. Even if you don't know, like say, how to get Python to connect to C, there's still plenty in a pure Pythonic or pure Julia or MATLAB, pure MATLAB space. Any of those different areas have opportunities that we'd love contributions on. And so those are two. The third sort of space is in maintaining and or developing new interfaces to tools. And so there's definitely a lot of opportunity there as well. I showed a slide earlier, see if I can get close to it, that had a lot of those included. Sorry, I keep coming back to the wrong thing. And so a number of different tools that are listed here. Some of those may not be taking advantage of the latest versions of Helix, and maybe some more streamlined interfaces that could help. So helping keep those up to date. Or if there's tools that you're of interest in bringing in that aren't on this list, then definitely would welcome contributions in helping develop those interfaces as well. And so then I think there's actually a fourth category of developer support that we'd love to talk further on, and that is a little bit on the usability space. I mentioned earlier that currently Helix is you often are kind of getting into a command line type of opportunity. There are some web-based helpers that are in there. But as we start to look towards growing this ecosystem beyond the research community, there's definitely a very real opportunity to have very user-friendly interfaces to pull these pieces together, leverage some of the interfaces that have been built, leverage also, I should highlight, we have established some common language to help make it easier to have interchange. So if you're doing a transmission, distribution, a production cost simulation or transmission, distribution, power flow dynamic simulation, what are the naming conventions between the different pieces? What are the unit conventions? Those kind of pieces we've established. And so helping take those, build them into interfaces and having nicer sort of perhaps even like drag and drop or other kind of interfaces for folks who may not want to be working at that command line level. Definitely some real opportunities there. If you're interested in engaging in any of those spaces, please reach out either to myself or on the Gitter channel, and we can get you connected with the right folks to get engaged. We'd certainly love some contributions and collaborations. Could even be projects that we can find funding for in that space too.
All right, and up next, you mentioned simulating potential latencies when managing DERs to address grid challenges. Can you say a bit more about that? How big of a challenge is this latency issue?
Yeah, great question. And as is often the case in these situations, it depends. Certainly, many control designs are very fast, and that would enable many of the types of behaviors. Like in this example, we're looking across a couple of minutes of time, where that delay becomes relevant in some perhaps not as carefully designed systems where there may be either bandwidth bottlenecks or so many handoffs between, say, a market operator sending signals out through some gateway AGC, connects into the aggregator. They have to churn it and then pass it through another network. Maybe utility gets involved, and somewhere down the line, it's working on the backbones of either interconnections of internet connections, but for customers or other devices. And some of the systems there, AMI, for example, weren't necessarily designed for real-time simulation. And the delays can start to add up into seconds. And that can be very relevant even for the somewhat slow phenomenon. Yeah, so certainly when we think about DERs, just to quickly recap those pieces, they're a slow phenomenon where some of the network latencies will become less critical. There's a lot of fast phenomenon, particularly when we look at advanced controls and coordination, whether that's peer-to-peer or even DERMS type systems, where some of the even second and sub-second type of phenomenon can matter, and those delays can really start to add up, especially on backbones like AMI and other systems that weren't designed for low latency. Those can be real bottlenecks, so it's worth capturing, at least verifying that things are going to work okay. And then I mentioned on the cybersecurity side before I got cut off, there's a real potential there too, where denial of service attacks, where folks, malicious actors, are intentionally flooding whatever network connection we have with so much traffic that it causes a bottleneck and can slow things down. Those types of delays can become very real, and we've definitely seen in some places in the field already too. So capturing those delays can become quite important in a number of different timescales when we start to think about DERs, and can also help us design the right control architecture that makes sense, and communication architecture behind that control architecture. That example I talked about with the EVs providing frequency response services through automatic generation control, the delays in there were modeled after realistic opportunities for control schemes. And I'd encourage you to either have looked at the deck when it comes up, or when you get a copy of those, there's a reference on a lot of the examples I showed, and they can dig into a lot of detail on exactly which network configurations providing which different types of latencies.
All right, so we have about 5 minutes left. We'll go to the next question. How has Helix been used for power grid and DER cybersecurity?
Fair enough. Well, we highlighted one example just now, where you can, very easily with built-in Helix co-simulation capabilities with the filters provide delays and other pieces. Those are very easy to configure. Beyond that, there's a number of other opportunities. I alluded to one earlier when I was talking about AI training. That was actually used in our cybersecurity type application as well, where folks were trying to train the simulations, trying to train an AI agent to be able to better understand anomalies. And we're suffering from a shortage of data. On the distribution side in particular, this can come from a lack of sensing ability, sensing deployment that's out there. But also it can come from, we tend to have a very limited set of weird conditions, if you will. The bad conditions, the anomalous conditions, thankfully don't happen very often. So they can be too small a training set for folks to work with. But by using co-simulation, we can simulate those non-ideal conditions, that outage condition, that weather condition, that super congested condition, that fault condition, whatever it happens to be, and really build up significant training data. And then that can be used, that example I was describing was for a cybersecurity application, to be able to train an AI agent to better detect anomalies. The other use cases, as I mentioned, Helix enables you to pull in communication simulation, both the simplified delays and the drop packets types of things that are built in, but also routing the information passed between simulators into more sophisticated simulations like NS3 or an OpNet or other kind of capabilities. And so we've done some use cases as well in that space where we're having the communication system being simulated in parallel to a broader network simulation, such that the communication backgrounds and exchanges are being routed as might be needed through Helix, or are providing through Helix, like the control signals are provided into a physical simulation. So Helix might be representing the grid and buildings on it and DERs, while a detailed packet exchange is happening in real time through an emulation environment. Scepter is one of those examples that we've used. And then, so that's being modeled. It could be cyber attacks happening in real time, malware being deployed in isolated environments, and then those control signals being sent over to a physical simulation through Helix to understand the implications on the model of what would do to the grid. So both of those are, all three of those examples. One, directly capturing some of the impacts of a cyber attack, such as delays from a denial of service. A second being the idea of training or other aspects for a kind of new and advanced AI type of anomaly detection that could have a cyber relevance. And then the other is just having a full up emulation of like a DMS system or other types of aspects that might be seen in a grid or aggregator performance, aggregator control system, having those control signals then interact with a simulated version of the grid or a broader energy system, and then understanding what the impacts are of that cyber attack that might be happening. So all three of those, and you can imagine more too.
All right, we only have time for about one more question here because we're almost at time. So final question, if you want to answer very briefly, is there a strong use case for developing an AI agent like GPT or Copilot for Helix?
That's an interesting question. There may be some opportunities. I feel like an alternative to, say, like a drag and drop UI, where if folks were able to have a GPT interface that said, build me this co-simulation that looks like this, and might be able to develop those configuration files we saw briefly on the Helix CLI slide. That might be an opportunity. It's one that haven't explored too much historically, but would be a very real opportunity. It could be that one step further in kind of human hands-on user interface development would enable a GPT-based development to be even more powerful. But there could be opportunities even today. Certainly feel free to reach out. It'd be interesting to connect and explore that further.
All right. Thank you very much, Brian, for that awesome presentation and discussion. And we'd love to see you guys next month on January 14th at 10 a.m. Mountain Time for Powered by EMIS. That'll be presented by researcher Bethany Frew. And with that, we're going to end it right on time here. Thanks again, everybody. We hope you have a lovely day.